Hey everyone, welcome to InsightsByRish. In today's video, I'm going to implement a project of time series forecasting, and for that I'm going to make use of this time series dataset from Kaggle of electric production. I will provide the link of this dataset in the description box. Now, this project consists of univariate data, that is, we just have a single column for which we have to perform time series forecasting. Soon I will make a video for multivariate forecasting where we have multiple columns and we have to forecast the values for all of them. I have downloaded the dataset and I have loaded the dataset here in the Google Colab environment. As you can see, electricproduction.csv. Now in first cell we will include all our libraries here. So let me write here importing libraries. Now we will include the libraries here as per our requirement whenever they are required and not right now, so that it will be better to understand that which library is required when. So first I will import pandas here. Let's run that. And let us also load that DF. So let us name that data frame as electric DF and we will say pd.read.csv. Here we have to provide the path of dataset. So let me copy the path from here and I will provide it here. Let us check the dimension of dataset now. So electric data frame dot shape. This particular dataset consists of 397 rows and 2 columns. If you want, you can even display that using the head method. So as you can see, this is our date column and this is the electric production column. Now the next task that we have to do, let me just use the info method here to display the data types of every column. Electric data frame dot info. Now as you can see here, our date column is of object data type and it is not an index, right? The index is some random range from 0 to 396. So the next task is to convert the data type of date column from object to date time and also to make that column as our index. So first thing that we will do here is converting the data type. Of date column from object to date time. So here we will say electric data frame and give the column name here, that is date. Then here we will make use of toDateTime method from pandas. So pd.toDateTime, and here we will pass the column which we have to convert to date time. So the column name is, and here we will pass the column which we have to convert to date time. So the column name is date from electric data frame. Let's run that. And let us again make use of info method to check the data type again, just to confirm. So now you can see the date column is having the date time data type, and this is what we wanted to do. The next task here is to make this column as our index. Right now the index is some random values initialized from 0 to 396, but we want this date column to be our new index. So the next task is resetting index. And here what we will do is we will say electric data frame, that is the name of our data frame. And here we will make use of setIndex method. So set index. And here we have to provide the name of column which we have to set as index. So the column name here is date, and also say in place is equal to true in order to make this changes permanent. Let's run that. And let us display this data frame here. Now you can see this date column is our new index. Now we don't have this random values initialized from 0 to 396. The date column is our new index, and that is what we wanted to do. Now after doing that, we have to check the seasonality, the trend in the data. As we have just a univariate column, we can directly use the plot method on this data frame. So here we will say plotting, and here we will say electric data frame dot plot and figure size. Now here you have to give the figure size, let it be 15,5, and let's run that. So as you can see, this is the plot for the column electric production, And let me also give the title here. The title is plotting electric production, and let's run that. Now we don't have this PLT right now. We have to import matplotlib here. So let me import matplotlib .pyplot as PLT, and now this will work. Now when you take the look at this plot, you can see there is some kind of trend and also there is seasonality. Firstly, we can see the seasonality here, as for specific time intervals the graph is going up, and again for specific time intervals it is going down. So there is definitely some kind of seasonality here, and hence we are making use of SARIMAX model. And then you can also find some kind of uptrend here. This is not a stationary data, this is an uptrend. So the next task is to convert this data into a stationary data. And though from this plot we can easily see that the data is not stationary, still we will confirm it by performing Dickey-Fuller test, actually the augmented Dickey-Fuller test. So let me write here augmented Dickey-Fuller test to check whether the data is stationary or not. Now to perform this ADF test, we have to import the required module for that. So here I will include from stats model .tsa.stat tools. I will import ED-Fuller. Let's run that. And now we will write a function here. Let me write it as def ADF-Fuller, ADF test actually. And here we will pass some data. Now this data will be our column name. Then we will say your result is equal to AD-Fuller. Now we will apply that AD-Fuller on the data. Here then we will print the statistics. So the first thing that we will print here is ADF statistics. And that will be stored in the result on index 0. And then we have to print the p-value. Now p-value is the most essential value. If the p-value is less than or equal to 0.05, then the data is stationary. But if the p-value is greater than 0.05, then the data is not stationary. So the p-value here, let's display that result. It's stored in result at index 1. And then we will also put if else loop here to display whether the data is stationary or not. So if the result at I, that is the p-value, so if the result at I, if it is less than or equal to 0.05, then we will say that reject the null hypothesis, because the null hypothesis basically says that data is not stationary. And as we are rejecting the null hypothesis here, which means we are accepting that the data is stationary. So let's say reject the null hypothesis, which means the data is stationary. And in the else block we will have that accept the null hypothesis, that is data is not stationary. Accept the null hypothesis, that is the data is not stationary. Let's run that. And now we will call this function. So let's say ADF-test, and here we have to pass the data, that is our column name. So we will say electric data frame, and from that we have to pass the column name here. The column name is this. Let's run that. And as you can see, it's giving us the p-value, then the whether to accept the null hypothesis or to reject it. So let me just fix this p-value variable once. Yes, so as you can see, the p-value is not lower than 0.05. It's actually greater than 0.05, which means the data is not stationary. So we are accepting the null hypothesis that data is not stationary. So before performing the SARIMAX, we have to make that data stationary. Now to make the data stationary, we are going to perform differencing here. There are various methods of making the data stationary, but we are going to make use of differencing here. Now, as this is a seasonal data, we are going to make a shift of 12. If we are working with non-seasonal data, then we can make the shift as per our requirement, like starting from 1 then 2. But as we are working with seasonal data, that is after every 12 months, we will make use of shifting of 12. So here I will say electric, if I am adding a new column here of shift 12, or we can say it as order 12. And here what we will do, we will say electric data frame, that is our data frame name. And from that, the column name, the original column name that we have, then minus, again we will write the same thing, whatever we wrote here, dot shift of 12. Let's run that and let us display the data frame. So as you can see, now you have this column of order 12. This column basically consists of values shifted by 12, that is the window size is 12. And why we shifted by 12? Because this is a seasonal data. Now after that, what we have to do, we have to again pass this column to ADF-test to check whether now this data is stationary or not. If it is not, then again we have to perform shifting. So I will again call this function here of ADF-test, and again we will pass that column as a data from electric data frame. The column name is order 12. Let's run that. Now as you can see, this is throwing an error because this order 12 column consists of NaN values. So we have to just make use of drop-NA method here. Now as you can see, the value, that is the p value, is less than 0.05. You can see that it is actually 8.8, but it is not 8.8. It is e raised to negative 0.7. It's basically in a decimal format with lot of zeros, preceding with lot of zeros. So this value is lower than 0.05, which means the data is now stationary. And now we will plot our stationary data. We will see how it looks. So let us say plotting stationary data. So what we will do here, we will again say here electric. Now here, when we were plotting, we directly said electric df.plot because there we just had one column, but now we have two columns and hence we have to specify the column for which we have to plot. So let's say order 12 dot plot, and I will give the same figure size here, which is 15,5, and we will also give the title here, that is plotting the stationary data. Let's run that. Now as you can see, the data is stationary. By that what I mean is the mean will be constant throughout this plot. Now as you can see, this data is a stationary data and you cannot find any uptrend or downtrend here. This is a stationary one, and this is what we wanted to do. Now, after making the data stationary, the next thing that we want to do, we actually want to build the model. But before that, in our model, we require the values of P, D and Q. Now the value of P is obtained from PACF, that is partial autocorrelation plot. The value of Q is obtained from ACF, that is autocorrelation plot, and the value of D is the value that how many times we perform shifting, this value. And what we have to do, we have to actually first obtain that P, D, Q values. So let's say here obtaining P, D and Q values. I will also show you the method how you can obtain that automatically using the Auto-Arima model. First we will see that manually. Now here we will plot the ACF and PACF plots, and first we have to import that. So let us go and import it. We will say from stats model dot graphics dot TSA plots. We will import plot ACF and plot PACF. PACF stands for partial autocorrelation and ACF stands for autocorrelation. After that, we will plot here. First, we will plot PACF. So here we will plot PACF. So let us say PACF is equal to plot PACF, and here we will pass our column name, that is the column that we shifted by 12. So let's say electric data frame, and the column name was order 12, and it also consists of null values, and hence we will make use of drop NA method. Let's run that, and as you can see here, we have to check the lags which are above the shaded area. The lags is, you can see the first lag, that is the significant lag going up to limit of 1. We have to ignore that because it's a 0. The next lag is up to 0.5, and that we have to consider. So that's first lag, and after that the next lag is on the line, that is on that line in the shaded region, so you don't have to consider that. So the lag that you are finding before the lag that is present in the shaded area is just 1, because immediately after the second lag, that is the lag at 0.5, you're finding a lag which is present in the shaded region. So here the value of P will be, let me say the value of P will be 1. You got the value of P. The same thing you have to perform for ACF. So we'll say plot ACF, and here we'll again pass the column name, that is order 12, and it consists of null values, hence we will make use of drop NA. Now as you can see, this is ACF, and from here we will obtain our Q value. Now the number of lags above the shaded region are the first significant lag up to going up to 1, that we have to ignore, and after that we have 3 significant lags that are above the shaded regions. So either you can consider 3, or you can even consider the first 2. So here the value of Q, let me say Q, either you can go ahead with 2 or 3. Now this is what we obtain manually by plotting the PACF and ACF plots. You can also obtain the optimal, or you can say the best value of P, D and Q using Auto-Arima model. And for that, what we have to do, first we will divide our data set into training and testing set before performing Auto-Arima. So train test split, and here what we will do, let's say train DF is equal to, now it will consider our training data. Now this data set in total consists of 397 rows, so we have to divide it by a percentage of 80-20. So around 80% of 397 would be somewhere around 315. So the first 315 rows will be included in the training data, and the rows after the 315, that is the 20% of the rows, will be included in the testing data. So we'll say electric DF starting from 350 up to the end. So this is our train test split, and now we will perform Auto-Arima here. So to perform Auto-Arima, first we have to import the module here. So we will say from PMD Arima, we have to import Auto-Arima. Let's run that. So right now it's saying that no module name PMD Arima is available here. So let me just install it again. pip install PMD Arima. Let's run that. And as you can see, it's successfully installed. We will again run this. Now you can see it's imported successfully. Now coming back to this code, we have to perform Auto-Arima here. So let's say stepwise fit. So we will be evaluating multiple parameters here, is equal to Auto-Arima, and here we will pass the main column, that is the electric column, electric production column from train data frame, that is IPG column. And here we also want the seasonal data. As you know, when we are performing time series forecasting using SARIMAX, there we have the order and we also have the seasonal order. So we also want the seasonal order, and hence we will say seasonal is equal to true. And here we have to specify the seasonal period. So we have considered the seasonal period of 12 months, and hence M will be 12. Let's run that. And let us print the summary of this stepwise fit. So stepwise dot summary. Now once you are done with that, next we will print its summary. And as you can see, this is our summary. It's giving us the best values for SARIMAX model. These are the order and these are the seasonal values. The seasonal span is of 12 months and hence it's 12. Then the p-value here we considered 1 and it is also showing that the value should be 1. Then the value for q, we said it should be either 2 or 3 and it's showing that it should be 2. So this is what we are going to perform, and these are our optimal parameters with which we will build our SARIMAX model. So here we will say building SARIMAX model. Now SARIMAX basically stands for seasonal autoregressive integrated moving average plus exogenous variable, and it's an extension of ARIMA model basically. So we'll say model is equal to SARIMAX. Now first we have to import that. We have to also import the SARIMAX module. So let me go here and import that. Let me say from that model dot CSA dot state space dot SARIMAX. I have to import SARIMAX. Let's run that, and then we will again come here and start building our SARIMAX module So here we will say SARIMAX, and here we will pass our training data, the training DF and the column from training DF, that is IGP, the sub column from training data. And then the order will be decided by this Auto-Arima. So whatever order we got from Auto-Arima, we will pass it here. So we'll just say the stepwise fit dot order. So stepwise fit is the variable in which we loaded our Auto-Arima, and whatever order it is giving us, we will put that order here. And we also require seasonal order here. So seasonal order is equal to, it is again extracted from the stepwise fit, that is from Auto-Arima. So let me say here stepwise fit dot seasonal order. Let's run that and let us fit that model now. Let's say a fitted model is equal to model dot fit. Now we are fitting the data on our and let's say DSP is equal to false. Now after fitting the data, let us print the summary of fitted model as well. So we'll say fitted model dot summary. Let's run that, and this is the summary of our fitted model. As you can see, the p value, the p greater than modulus z value is 0.00 everywhere. It's good. The value, whenever you are fitting your model, the value here in your summary should always be lower than 0.05. Now after fitting the model, next thing we have to do is we will make some predictions. So what we will do, let me display the test data frame once. So this is our test data frame where we have the original column and the order 12 column. Now here we have to append one more column consisting of our predicted results. So first we will make predictions here. Let's say predictions, and we'll store that predictions in a pred variable. So we'll say fitted model dot predict. Then we have to give start and end here. So we'll start from the first row itself. So the first will say test underscore df dot index from first row itself, and hence 0, and end we will go up to the last row, and hence it will be test underscore df dot index -1. Let's run that and let me display the predictions here. So these are our predictions for the date time, and we have to append these predictions now in the test data frame column. So let's do that. Let's say test and create new column named as SARIMAX predictions, and we'll append the results from pred here. It's actually test data frame. Now let me display the test data frame here. Now you can see we have one more column here of SARIMAX pred. So now we will plot the original column and the predicted column, and that is the forecasted column. So here we will say plot. So first is plt.plot. Here we will say test.index, that is test data frame dot index. Now our index is date time. So on x-axis we will basically have our date time, and on y-axis we want the values from the original column here. So test data frame, the original column here is IGP, and then the label here will be actual values. And we also have to set the figure size here. So let's say plt.figure fig size, and let's say 15,5. Now this plotting was for the actual values. Let's just run that. So as you can see, these are your true labels. Let me say here legend. So now it will also show you the legends here. As you can see, this blue line is for actual values. Now we have to plot our forecasted values, and we have to see whether they are matching to this actual values or not. So we'll say plt.plot. Now the x-axis, that is the index, will remain same. Even for the predicted or the forecasted values, the x-axis will be the date time. So we'll say test df.index. It will remain same. And on y-axis, we will have the SARIMAX predicted column from the test data frame. That is the forecasted values. And let's label that as forecasted values. And let's run that. Now, as you can see, this orange line shows the forecasted values and the blue line shows the actual values. So you can see somewhere there is a difference and somewhere they are very close to each other. But basically, it's capturing the trends and the patterns from the original data points. You can see the patterns and the trends in the original values are very similar to that of the forecasted values. So the model is working good and also making the forecasting efficiently. We can even add the title here, plt.title, and the title would be, let's say, comparing actual and forecasted values. Let's run that. So here you can see this is a plot where we saw that the model is performing really very well because the forecasted values are very similar to that of actual values. And we built this model using SARIMAX because we had seasonal data, and we performed autocorrelation to obtain the appropriate and optimal values of P, D, Q parameters. So soon I will also make video on multivariate forecasting where we will have multiple columns in our dataset. So that's it for the video. Thanks for watching.